Hi, Science 7. Topic 5 today about changes in state. So, we know that when materials are heated up, temperature changes, they will expand in different amounts, and they will also contract when they cool down in different amounts. So, we had talked about the lengths of different metals and how they changed. They all expanded when they were hotter, but to different amounts. And so this slide just shows you how gold heats up actually 7 times faster than aluminum. So we're talking about how much more quickly some conduct heat. So definitions here: heat capacity is how much thermal energy or heat that the takes to increase the temperature of a substance 1 degree Celsius. And so it may take more heat, for example, to heat a pot of water than if you were comparing that to heating alcohol. Would be a lot faster. So the mass that you're looking at and the material are two considerations when you're looking at heat capacity. When we see the term specific heat capacity, we are talking about just 1 gram of that material. So taking 1 gram of something and increasing the temperature by 1 degree Celsius is specific heat capacity. So if you have a low specific heat capacity, it means you heat it up and the temperature goes up very quickly, like I was mentioning would happen with something like alcohol. If it has a high heat capacity, that means it has like a high amount of heat that it can hold. Capacity is like how much it can hold. So if you heat something up over and over for quite a while, and it doesn't change much in temperature, then it has a high heat capacity. And this would be something like water. So if you've ever stood there and watched water boil, it's pretty boring because you have to add quite a bit of heat for it to change 1 degree Celsius. So water then has a high heat capacity. The temperature of oceans barely change all year round because of the heat capacity being so high. It would take a lot of heat from the sun to change at that 1 degree Celsius, so it barely does that ever. And there's so much water in there. This activity, the hot stuff activity, is from your textbook, page 219. I'll let you go have a look at that. You can check out the answers that are posted here. But if you don't have your textbook at home, I did post the activity from page 219 right on your classwork page in Google Classroom. So you can basically compare how water has a high heat capacity because of how much it takes to heat it up, comparing that to sand that has a low heat capacity because it doesn't take much to heat up sand and make it like very painful to walk on a hot day. So you guys can check that out. Answers are posted here. 3 states of matter looks familiar to you. We've talked about this before. Solid, and here's our descriptions. Liquid takes the shape of the container. Gases takes the shape and the volume of the container. So what we want to look at is the comparisons of what the terminology is when states change. When we go from solid and melt something, that would take energy. Liquid and evaporating it into gas, that would take energy. So we're using it for those. Whereas if gas is turning like compressing into a liquid, or a liquid freezing into a solid, for this one energy is released. So basically you can imagine how it would take energy to melt an ice cube, and how that would be opposite if you were basically putting liquid water into the freezer to freeze it into a solid. You would have to get it, it would be colder to do that, so you're releasing energy for that. So looking at this picture here, you can see that solid, liquid, gas. Solids looks like an ice cube, liquid looks like liquid water, and gas looks like vapor here. And these terms that you have to know is, some of them are very obvious, like taking a solid ice cube and turning it into liquid water. You know that is melting. It is also called fusion, so you should know that term as well. And if you take the liquid water and evaporate it, take a cup of water and leave it on the counter for a week, there may not be any water left. That is evaporation, where it turns into a gas. And on the other side, if you exhale onto a mirror, your water vapor gas from that you're exhaling will condense into a liquid, just like evaporated lake water will condense as clouds of water droplets in the sky. Same kind of deal, condensation. And of course, if you take liquid in your ice cube tray and put it in the freezer, it will freeze and turn solid. So you could call it freezing, or you could call it solidification. Now, if you skip a step, and either a solid, like this could be example of dry ice that evaporates and turns all fizzy and bubbly and smoky. We've seen that in class at Halloween. That is called sublimation, but so is something like frost, where there's water vapor in the air and it freezes as frost on your windshield. That is also called sublimation. So solid to gas or gas to solid both are given that name. So those terms are a big part of this chapter. The next few pages of notes just goes through each part individually. This one from solid, again, melting it if it turns to liquid, or freezing it if it turns solid. And it says that this would happen at the same temperature, and we know that to turn something into ice, we're looking at 0 degrees Celsius. Here, evaporation, turning something to a gas. It also says here that it happens at the same temperature. For this one, to take liquid and make it evaporate as a gas, it's can be evaporation, opposite condensation. And if we're looking at water, it says that this could happen at the same time. So around about, for this one, it would be 100 degrees Celsius, depending on where you are from sea level, but that's kind of the general amount. Sublimation, we skip the one step of the liquid step and go solid to gas or gas to solid. Just to review, here's some sublimation happening of iodine. You can check out the video. And my suggestion is that you draw out this whole chart with the words missing so that you can practice all of the terms. On bottom page 16 of your notes, there is a spot to draw the a picture, and I posted it in here. It's about evaporative cooling, and it's what this page is about. And basically, it says that the reason you feel cold when you step out of a lake is because the water droplets left on your skin are going to be taking the heat from your body and evaporating those water droplets. So it's taking heat from your hand, from your skin, leaving you feeling cooler. And so some of it is evaporating, as you can see here, and going into a gas state. And that's what takes the heat from your body and makes you feel cool. And if you have ever maybe, thought of having like a cotton ball of alcohol on your hand, compare that to water, you'll feel more of a cooling sensation with the alcohol because it's going to evaporate more quickly and have more evaporative cooling. More quickly take heat from your hand. So what they say is when states are changing, the particles are rearranging, and if the energy goes up, they become less organized. So you can see solids are more organized. You heat it up and becomes liquid, less organized. Heat it up, it becomes a gas, less organized, kind of bumping around, those molecules do. So they say when the change of state is happening, the temperature isn't changing at that time. So you can heat up some water, for example, from frozen, you can heat it up and you see the temperature is, if you can imagine the temperature of water going up, for example, but when it actually starts evaporating, during that evaporation stage, the temperature stays constant. So it doesn't, the energy of the particles doesn't change, the temperature just does not change when they are changing state. So they're, that's when it will be constant in those times right there. And those are the times, for example, that we will see in those specific areas, for example, that gas will turn into liquid, or solid will turn into, our liquid will turn into solid. And so those changes right there will be times when the temperature is constant during that time. So water boiling, as we see the steam coming off, will not change. The temperature that you measure will stay constant until all the water is gone. Then when it's just steam left, the steam can get hotter and hotter. So we need to know melting and boiling points, and just the fact that they are not all the same for all substances. As you can see here, water melts at 0, boils at 100. We know those for degrees Celsius. We notice that there's some very high melting points and boiling points for the metals, and really low for something like a gas like oxygen. Very low melting and boiling point. You won't have to know all of those, just know that they're different for different substances. Evaporative cooling is what we talked about already, and so there are energy will let some, like the heat from your skin, will let some molecules escape and evaporate, and the slower ones will stay behind. So there'll be some liquid left behind, and when you are perspiring or sweating, what happens there is your body's trying to cool you down, so it puts some perspiration, some water on your skin that will then take some heat from your skin in order to evaporate and leave you feeling cooler. It's a way to cool you down. So plateau problem is an exercise in your notes that you can check out, and basically we're looking at at how we've got the graph here with things added in. As you warm something up, solid will start melting, but in that melting stage the temperature stays constant. When it's all melted, then you can see that it would warm up, but as you start evaporating it, it will stay a constant temperature until it's all evaporated. Once it's all liquid and you have, all evaporated as to gas, the gas that's left can go up in temperature. So our liquid can go up in temperature, our gas can go up in temperature, but while the state is changing, the temperature is constant. Here you can see as you turn something into a gas, it's getting more energy. Those molecules are starting to move further apart. As you cool something down, they're starting to slow right down. As you, for example, take liquid and make it into an ice cube, you're going to have the energy releasing, and it's going to get less energy and be more, those solid particles stay kind of more stationary. Okay, so the latent heat stage, this is the one we talk about that is times when bonds are breaking, but because the speed isn't changing, the temperature remains constant. So this would be during the, for example, melting time or vaporizing time. There is heat that would be continually going in. It's like having a pot of water on the hot plate and just starting with frozen ice and going through all the stages. But while the state is changing, you're adding heat, but energy is being used to break bonds. And so that's why you don't see a temperature go up. It stays constant. It's because they call it latent or hidden heat. So we can see here that ice will stay at 0 for a long, long time. Once it's melted and you have all of it as liquid, then you'll see the temperature going up at that point. That's a review of the arrangement of the particles that we saw in the last chapter, and a fun little video to finish off with here. So I am going to wrap up, and you guys can check out the review pages in the end of chapter 5, topic 5, and I will